Polar form example. Represent the complex number z equals to 1 plus I in the polar form. In order to explain this complex number, what I'm going to do, I'm going to graph this complex number. So if I graph, as we can see, my real part is 1 and my imaginary part is also 1. So if I write the complex number in order here, I will write 1 comma 1. So let's graphically represent that complex number. So this is my x-axis, let this is my y-axis, and let this is the point P with coordinate 1 comma 1. If I connect this point P with origin, I will get this line, and this is basically my complex number z equals to 1 plus I. Let this line makes an angle of theta with origin. So basically you have this complex number making an angle theta with x-axis. Now let's write the complex number in polar form. So polar form of a complex number is given as z is equal to r inside the bracket cosine theta plus I sine theta. So if I simplify, what will I do? I will distribute r inside the bracket, and if I do that, I will write z is equal to r cosine theta plus I r sine theta. Now what I'm going to do, I'm going to compare this equation with the actual complex number. So I will write the actual complex number below this one, which is basically z equals to 1 plus I. Now let's compare, and if I compare, I will get r cosine theta, which is my first equation, and r sine theta equals to 1, which is my second equation. So basically I have two equations, one is right here and equation 2 is right here. Now let's square and add these two equations, and if I do that, I will write r cosine theta square plus r sine theta square is equal to 1 square plus 1 square. If I further simplify, I will take r square outside, and inside the bracket I have sine square theta plus r square cosine square theta is equal to 1 square is 1 plus 1 square is again 1. If I further simplify, I will take r square outside, and inside the bracket I have sine square theta plus cosine square theta is equal to 2, because 1 plus 1 is 2. As we know, sine square theta plus cosine square theta is 1, so I will write r square is equal to 2, because r square times 1 is r square, so I will get r square equals to 2. If I further simplify, I will write r is equal to square root of 2, where r is greater than 0. So basically, I'm not considering the negative value of r. Now, let's substitute the value of r equals to square root 2 in equation 1 and 2, and if I do that, I will get root 2 cosine theta, which is my first equation, and root 2 sine theta equals to 1 is my second equation. So what I'm going to do, I'm going to consider one equation at a time, and then I will solve that equation. So first of all, I'm going to consider the first equation, which is basically square root of 2 cosine theta is equal to 1. If I simplify this, I will write cosine theta is equal to 1 over root 2. If I want to find the trigonometric value of theta, I will get theta equals to pi over 4. Now let's simplify the second equation, which is basically square root of 2 sine theta is equal to 1. If I simplify this, I'll write sine theta is equal to 1 over root 2, which will give us theta equals to pi over 4. So basically, as you can see, the value of angle theta is pi over 4. So we will write the modulus of the complex number is r equals to root 2, and the argument or the amplitude of the complex number is theta equals to pi over 4. Now let's write the complex number in polar form. And if I do that, I will write z equals to r inside the bracket cosine theta plus I sine theta. Now let's substitute the value of r equals to root 2 and theta equals to pi over 4 over here. And if I do that, I will get z equals to square root 2 inside the bracket cosine pi over 4 plus I sine pi over 4. And this is my complex number in polar form. And this is how we can convert any complex number in polar form.